Hello everyone and welcome to another lecture on probability. So in this lecture, we'll take a look at parameter estimation using mainly a method known as maximum likelihood. This ML is not the same as machine learning. Maximum likelihood is older than machine learning, but maximum likelihood is one of the key tools used by machine learning. So ML uses ML. So what is parameter estimation? So here is the setting of parameter estimation is as follows. It is where you have a family of distributions. You don't have a single distribution, but rather a family of distributions. So that's typically denoted as script P, and a family of distributions parameterized by theta, right? So let's say P theta. And your theta takes values in some parameter space, capital theta. So what you have is a family of distributions. So we will see several examples of this pretty soon. What you have is, you can just view it as a collection or a set of densities or distributions. So you have such a object, and you have data x1, x2, xn drawn IID from some x1, x2, xn drawn IID from some p theta for theta belonging to theta. You have your data drawn from some element in this family, but you don't know which. The goal is to use this data and find out what is the best theta, right? So you use this to estimate the true theta. Theta represents the parameter, and from data can you estimate the true parameter theta. So that's the parameter estimation setting. How do you estimate the parameter of the distribution from some finite amount of data? So there are several ways in which you can do this, but the most popular and the most prevalent method is what is called maximum likelihood. So it's based on a very simple idea. So if your theta was given, so you have data x1 to xn. So you can define what is called the likelihood of a parameter theta. L of theta is simply equal to the probability of x1 equal to x1 xn equal to xn given theta, right? So now if theta were given, then you can compute this, right? So I'm going to be using this notation for both discrete and continuous, even though for continuous this is strictly not correct, right? I should use the density, but I'm going to use this, right? So this effectively is saying that is f x, right? So I'm going to use the same thing for probability mass function and density function. So this is the idea. So what is this capturing? This is capturing for any given parameter theta, I can measure how likely is this data, right? So sorry for that. So for any given parameter theta, what is the probability of this particular data set being generated? I can measure that, and I will choose the parameter for which the probability of this data being generated is highest. That's the reason why it's called maximum likelihood. So this is likelihood. This L of theta is term called likelihood, and you want to choose the parameter theta which maximizes the likelihood. So let's do some simplification. For the simplification, we have assumed that x1 to xn are independent, right? So this essentially boils down to product over I equal to 1 to n fxi of xi given theta, right? So theta is the parameter and fxi of x given theta. And what is that? That's exactly equal to product over I equal to 1 to n p theta of xi. Recall our family of distributions was parameterized by theta, right? So p theta of xi. You want to maximize this, but you have a product term here. That's an ugly thing to maximize. Is there an easy way you can do that? Well, you can take the log of this. Instead of maximizing the likelihood, you can maximize the log likelihood. If you did that, log of L of theta is sum over I equal to 1 to n log of p theta of xi. So this is the log likelihood. Maximizing the likelihood is the same as the maximizing the log likelihood because log is a monotone function. Sometimes you might, instead of maximizing the log likelihood, you might minimize the negative log likelihood. Let's call the risk function r of theta to be the negative log likelihood, which is minus log L of theta. So you can easily see that maximizing the log likelihood is the same as minimizing the negative log likelihood. So that's so it's just an issue of which you are comfortable with. Are you comfortable with maximizing or minimizing? But they are really the same object. So if you can find the theta which maximizes this particular sum, that is your estimate of the parameter. Is that the true parameter? We'll never know. I mean, because the moment you have probability, we can never be sure of this, but we can give the most likely parameter that generated this data. Right. So let's see some examples. Let's take the simplest example, which is the case of Bernoulli bias. So in this case, the the family of distributions P is simply Bernoulli with bias theta, where theta is in the range of 0 to 1. Okay. That's your family of distributions, this Bernoulli theta. And you have a sequence of, let's say, coin tosses, x1, x2, dot, 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 xn. All of these are either 0 or 1. Right? That's either heads or not heads. So it's 1 or 0. From this, can you estimate the parameter theta, right? So you can immediately see that you can never get the true theta. Even if you had 1 million coin tosses, you can measure, you can estimate the bias of the coin, but can you be certain? Can you be 100% certain that it was a fair coin? Right? You can never be certain. Maybe it was 0.51, maybe it was even 0.6. Just by randomness, it so happened that in a million coin tosses, it happened in the way it does. You can never be 100% certain. The moment you are entering the realm of probability, you can never be 100% certain anyway. Right? So all of this will be with respect to certain uncertainty. But you can still find the maximum likelihood parameter, which is a reasonable thing to do. So let's find the maximum likelihood parameter for this. And the answer you will find is a very natural solution, but we'll try to get that in a dense way. Right? So now first, what is p theta of x? P theta of x is equal to theta if x is equal to 1 and 1 minus theta if x equal to 0. Okay? So it heads with probability theta and tails with probability 1 minus theta. So heads means 1, tails means 0. This is fine, but we can write this in a more compact way as follows, which is theta power x into 1 minus theta power 1 minus x. So note that this particular way of writing is exactly the same as this. Right? So x can take values only 1 or 0. If x equal to 1, this would be theta power 1 into 1 minus theta power 0. So that's theta. If x was 0, this would be theta power 0 into 1 minus theta power 1, which is 1 minus theta. So this case expression is written in a compact way as like this, theta power x into 1 minus theta power 1 minus x. And this makes sense because x can take values only either 1 or 0. Okay, so now we have p theta of x. Now let's write down the negative log likelihood, which is r of theta, which is the negative log likelihood, which is minus sum over I equal to 1 to n log of p theta of xi. Right, let's copy this and continue the next page. Oh, sorry, I'll have to create a another page. That another page is created. Right. So this is this is the negative log likelihood, and we have already written p theta of xi. I'll move this a little bit to the left. Right. So let's go ahead and simplify this further. This is minus sum over I equal to 1 to n log of theta power xi into 1 minus theta power 1 minus xi. And you can immediately see why we did this, because log nicely decomposes products. So this we can write as sum over I equal to 1 to n minus sum over I equal to 1 to n xi log theta plus 1 minus xi log of 1 minus theta. This minus is common across everything. If you we can further simplify this as follows: sum over I equal to 1 to n xi log 1 by theta plus 1 minus xi log 1 by 1 minus theta. Let's simplify this even further as follows. So sum over I equal to 1 to n. Let's call sum over I equal to 1 to n xi as the number of heads, right? Let's call that a. Right, for simplicity, let's call that a. So it's a times log 1 by theta, and sum over I equal to 1 to n 1 minus xi is simply the number of tails. That's going to be equal to n minus a plus n minus a log 1 by 1 minus theta, where a is the number of heads. A is equal to sigma xi, the number of heads. Now you want to find a theta which minimizes this. What theta minimizes this? This you might have seen in your optimization module. The theta that minimizes this is exactly given by, it's a very natural thing. This theta which minimizes this is the ML estimate, the maximum likelihood estimate. This theta hat ML is simply going to be equal to A by N. Apologies for that. Theta hat ML is simply given by A by N. Just create another page here. Theta hat ML, which is the minimizer of the previous thing, is simply given by A by N. This is a natural thing here, which is sum over I equal to 1 to N xi by N. So it's simply the fraction of the number of fraction of heads. That's your ML estimate, which is a natural thing to do. You might have already done this even without the ML estimate, but ML estimate gives you a formal way of saying that the most the parameter which most explains the data is given by simply the sample mean, or the number of the fraction of heads in the number of coin tosses. So let's do one more example where we have x, your p theta, your p, your family of distribution p is simply given by uniform of a comma b, where your a and b are reals. So now there are two parameters here, not a single parameter, but rather two parameters. Your theta in this case would correspond to a vector if you want. It's a two-dimensional vector. Theta corresponds to all the parameters, in this case a and b. So now you have uniform a and b, and you have data. Your data d is simply given by, let's say you have data x1, x2, xn. So what is the maximum likelihood estimate for a and b given this data? you might already have an answer in mind, and you will see that the answer that you get at the end of this is also most likely matches your answer in mind, and it's a very intuitive answer. Right. Now what is p theta of x first? Right? P theta of x is simply given by 1 by b minus a. Theta, I'm going to use theta as effectively a comma b. Right? So theta represents both a and b. So 1 by b minus a if x belongs to a to b and 0 otherwise. So you have your p theta given as follows. Now we can get the negative log likelihood function, which is your the risk of theta, as simply minus some more I equal to 1 to n log of p theta of x. So the same way we simplified p theta in a product form, you can do the same thing here and say p theta of x is simply 1 by b minus a into the indicator of x belongs to a to b. This expression is exactly the same as the previous expression, but just that this is more compact and expresses in a product form. And the product form expression is nicer because log decomposed it even further. Right? So let's write down the risk of the parameter theta as follows. So if you go ahead and write down your negative log likelihood, you want to minimize this function r of theta as simply sum over I equal to 1 to n minus log p theta of xi, right? So p theta of xi was simply xi belongs to 1 by b minus a into indicator of xi belongs to a to b. Let's decompose this even further. This is equal to sum over I equal to 1 to n minus log of 1 by b minus a minus log of indicator of xi belongs to a comma b. So now we have r of theta expressed as follows. What can you say about this function? Right? If you have even if one of the xi's does not belong to a comma b, this is going to be equal to 0 and log of 0 is going to be minus infinity. Right? So, minus log of 0 is going to be, log of 0 is going to be minus infinity, minus log of 0 is going to be plus infinity. So you can't have your xi, your a, b such that not even a single xi should be outside the limits. So we can, however, now if we have that, if a is lesser than min over xi and b is greater than max over xi, right? So if this is not true, then you have the r of theta is going to be equal to infinity, right? This is a finite term anyway, and you have if this particular clause is not true, then r of theta is going to be infinity. So you want to minimize the negative log likelihood, so you don't want to choose such a theta, right? So now without loss of generality, we can choose a to be less than min of xi and b to be greater than max of xi. If we do choose that, then this term is always going to be the second term is always going to be equal to 1. So the log of 1 is going to be 0. It's going to completely cancel itself. So r of theta is simply n times log of b minus a. So you want to minimize this. So you have n times minus log of 1 by b minus a, simply n times log of b minus a. So you want to minimize this term. You want to choose a and b, which minimizes this. So you want to minimize b minus a. The only way you can do that is by setting a to be equal to min over xi and b to be equal to max over xi. So this particular value of a and b is the maximum likelihood estimate of the data. So given a bunch of data points x1 to xn, the ML estimate for a is simply min over xi, the ML estimate for b is simply max over xi. This is a pretty natural estimate, but now we have derived this from first principles. Let's move on to another example where we have normal mean. Now the parameter, your probability, your family of distributions P is simply, let's say, normal with mean mu and variance 1. The variance is a constant, variance is not a parameter. Your mu belongs to R. Now this is your parameter theta is simply equal to mean mu. You have data points x1, x2, dot, 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 xn. Each of these xi's are real value. What is the ML estimate of the parameter mu? What is p theta of x? Well, that's simply 1 by root 2 pi x puff minus half into x minus mu the whole square. Right? So theta and mu I'm going to use interchangeably because theta is the general parameter, mu is simply the notation I'm using for the case of the normal random variable. Right? So p theta of x is simply 1 by root 2 pi x puff minus half into x minus mu the whole square. This is simply the density function of the normal random variable. What is your risk of or the negative log likelihood of theta? It's simply equal to sum over I equal to 1 to n minus log of 1 by root 2 pi into x puff minus half into xi minus mu the whole square. You can once again use the power of the log, and you have log of 1 by root 2 pi, which is a constant, right? Which does not depend on theta, or theta in this case is simply mu. So minus log 1 by root 2 pi is something which does not depend on theta. We'll just ignore that. We'll just take terms which contain the parameter theta or mu, right? So which is now, which means that we have sum over I equal to 1 to n. So you have minus log here and x here. Log and x really cancel out each other, and you have the two minus signs also cancel out each other. So you end up with r of theta is equal to sum over I equal to 1 to n half xi minus mu the whole square. This is your negative log likelihood function. You have some constants which don't depend on the parameter mu. We'll just collect that together as a constant here. So what value of mu minimizes this? Well, in this case, it looks like a function of mu. How do you find the mu which minimizes that? You can use your first order necessary condition. You can take the derivative of this with respect to mu and set to 0. And those are critical points. Your minima has to be one of these points. In this case, it happens to be that there is a unique point. So you can just solve for it and you get the minimum. Right? So if you set your r dash of theta to be equal to 0, then you would get sum over I equal to 1 to n xi minus mu to be equal to 0, which implies mu to be equal to 1 by n sigma xi. This is also a very natural looking parameter. That is, you choose your ML estimate of the parameter mu is simply equal to the sampled mean, say 1 by n sigma x. Right, so that's your ML estimate for the normal distribution. Now let's do one more final example and wrap up. Your parameter family P is simply the set of normal distributions with mean mu and variance sigma squared. Right. So you have mu belongs to real and sigma squared belongs to positive values. Right. So you are forced to choose positive values for the variance. We'll actually have sigma squared, but sigma squared itself we will use it as a variable. We will not try to find sigma, but rather sigma squared itself. We want to find the ML estimates for the parameter mu and the parameter sigma squared. Once again, what is the data going to look like? The data is going to look like x1, x2, xn. You have n data points. Each of these data points are real value. What is the ML estimate of we'll first write down what is p theta of x. P theta of x is, here you have the variance sigma is not 1, so you can't ignore that. So you have 1 by sigma, and it's also a parameter. You have 1 by sigma square root of 2 pi into x puff minus 1 by 2 into xi minus mu the whole squared by sigma squared. So this is your p theta of x. Can we just use ML principle, the likelihood principle, to get that, right? So what is the negative log likelihood? R of theta. Here theta, the parameter here, corresponds to the both mu and sigma squared, right? So I'm going to use theta as a package which contains both mu and sigma squared. Oh, sorry. Let's need a couple more pages. So what is R of theta? R of theta is sum over I minus sum over I equal to 1 to n log of 1 by sigma square root of 2 pi plus minus, strictly speaking, minus half into xi minus mu the whole squared by sigma squared. So this minus is common for both these terms. So here when you had just the mean, you could just ignore this term. Why is that? Because this term happened to be just a constant. But when you have sigma also as a parameter, you can't ignore this term, and you have to take care of this also. Right? So let's just first copy paste this and continue in the next page. So let's go ahead. But you can ignore the 1 by root 2 pi because 1 by root 2 pi is a constant. Right? So you end up with the n times log sigma. So you have 1 by sigma and minus, so cancels out to get n log sigma plus half sigma xi minus mu the whole squared by sigma squared. This sum, this sum sigma and parameter sigma looks confusing, but I'm going to just say that sum over I equal to 1 to n xi minus mu the whole squared by sigma squared. So this is your R of theta. Now you have two parameters, mu and sigma squared. Let's first take you can do the same thing again, right? You want to find the mu and sigma squared, which minimizes this. So let's do the critical points thing, right? So let's take the derivative of this with respect to mu and sigma squared and set it to 0 and see we can solve those two equations. Let's first set the derivative with respect to mu and set it to 0. So we have dou r by dou mu would be the first term. If you do that, the first term becomes 0 because there's no dependence on mu. So the second term would be sum over I equal to 1 to n xi minus mu by sigma squared. So the half and 2 cancel out each other. Sigma squared stays here. Xi minus mu the whole squared becomes 2 into xi minus mu. So the 2 and a half cancel out. Right? So we have xi minus mu by sigma squared. Right. So which means that if you set this to be equal to 0, then the equation is mu would be equal to 1 by n sigma xi. Right? This is something which you had seen already. You set your mean to be equal to the sample mean. Right? This is the first equation for setting the gradient to 0 and finding the critical points. In this case, again, you will find that there is only one critical point, and that does happen to be the minima of the negative log likelihood. So now let's take the derivative of r with respect to sigma square and see where we go. So let's take the derivative with respect to sigma squared. So if you do that, we have a sigma here. It looks ugly. So instead of doing that, we can use n by 2 log. Instead of having n log sigma, we'll just call it n by 2 log sigma squared. Right? So this is simply the property of the logarithm. We can do that instead. N by 2 log sigma squared plus half sum over I equal to 1 to n xi minus mu the whole squared by sigma squared. Right? Let's once again copy this for simplicity and take the derivative with respect to sigma squared. Okay. So if we take the derivative with respect to sigma squared, dou r by dou sigma squared would be equal to n by 2 into 1 by sigma squared plus half sum over I equal to 1 to n xi minus mu the whole squared. So this is a constant as far as we are concerned. Now xi minus mu the whole squared is a constant. So xi minus mu the whole squared into 1 by sigma squared. 1 by sigma squared, if you take the derivative with respect to sigma squared, it would be minus 1 by sigma squared the whole squared. 1 by x, the derivative of this is minus 1 by x squared, so minus 1 by sigma squared the whole squared. So now if you take the derivative of with respect to sigma squared and set it to 0, you get 1 by n by sigma squared is equal to sum over I equal to 1 to n xi minus mu the whole squared by sigma squared the whole squared. So one of the sigma squared terms cancels out, you get sigma squared simply equal to sum over I equal to 1 to n xi minus mu the whole squared by n. Right. So this is your second equation. You can solve the first and second equation together and you get your mu to be equal to the sample mean and your sigma squared to be equal to the sample variance computed using mu, the empirical mean as the empirical mean as the mean, right? Or mu is equal to the sample mean and sigma squared is equal to the sample variance. So those happen to be the ML estimate for mu and sigma squared for the case of the normal family with mean and variance as the parameters. So the ML, we have seen some very simple examples of maximum likelihood, and these form the building blocks. But you can see even for very complicated models, the maximum likelihood forms the first point from which you build on more complicated algorithms. We will see such an example in the next class where we will define a pretty complicated model known as the Gaussian mixture model and how the parameters estimation for that is very similar to a very fundamental machine learning problem called the clustering, and how we can apply the maximum likelihood method for solving that particular estimation problem. With that, we can wrap up this class.